All right, we are going to look at pendulums today and some of the stuff we can find with them. So the first thing we're going to start off with is we're going to start with finding the initial height of a pendulum that's been swung out to some angle. Now the reason we need to find that height is when we go to talk about energy in the work kinetic energy theorem, we're going to need to know that height for the potential energy function. Okay? So the second thing we're going to do is we're going to find out if I start at this angle and swing it down, how fast is it going at the bottom when it reaches its maximum speed. Last thing we're going to do is we're going to go back to forces and we're going to think about radial forces, and we're going to find the tension in the string at those 2 points, at the starting point and the ending point. So those are things we're going to do today. So the first thing is finding height. So this is more of a geometry exercise, so let's get into it right away. So when I talk about finding the height, I can think about point 1 and point 2 here. I will label them for us. And what I want to do is I want to consider point 2 to have a height equal to 0. And I essentially want to figure out what is the height of point 1. And so a good place to start is to draw that height right here and say that's the height I want to find. How am I going to do it? So what I can think about is I do have a triangle here, and I can find this side of my triangle. Here I'm going to call x. Once I know that side of the triangle, the length of my pendulum has not changed. It's still L. So in order to find H, what I'm going to do is I'm going to take L and I'm going to subtract that X value. That X value I'm going to get from this triangle here. And so I'm going to have H is equal to L cosine, L minus L cosine of my angle. So this is my angle with the vertical in this case. I can factor out an L, so H is going to be L times 1 minus the cosine of the angle. In this case, I can plug in my 60 degrees and my 0.8 meters. And so I have H is equal to 0.8 times 1 minus the cosine of 60. And so my height comes out to be 0.4 meters. All right, so the next step is we're going to set up a work kinetic energy problem using that height to find how fast it's going at the bottom. So we're going to walk through the work kinetic energy theorem. So I'm thinking about it being released from rest at that angle of 60 degrees and swinging down, and how fast is it going to reach the bottom. So as it's swinging down, there are no applied forces, so we have no input work. There is no friction to speak of. It's not sliding on a surface, or air resistance is negligible. K2, so it does have kinetic energy at my point 2, so that's there. K1, oh, it is stopped there, so the velocity at point 1 is 0. And again, if you want to, you can write stuff under here like no applied force. You can write no friction. You can write V2 equals 0. Okay. So at point 2, the height is 0, so there's no potential energy there. It does have a height at 1. We just found it to be 0.4. And then there are no springs here. Okay. So my equation kind of narrows down pretty quick here to 0 is equal to K2 minus UG1. So I have 0 is equal to 1/2 mv squared minus mgh. And we are solving for v, so let's move that mgh over to the other side. So I have mgh equals 1/2 mv squared. Yes, your m's do cancel. Multiply the 2 over, and then take the square root. So v is going to be the square root of 2gh. Now I know this should be a plus or minus. We're just finding speed with our work kinetic energy theorem, so it is going to be a plus value. H, I did find, if I was going to write more of the generic form of that, I would plug this value in for h, and so my speed would equal the square root of 2g times L times 1 minus the cosine of the angle. And so from that, this does have a limitation, of course, and the limitation kind of lands in that it's between 0 and 90 degrees. Once we get above this, even when we get up to that very top there are some issues we do run into with using a pendulum at those angles. Okay. But I can plug in my values, and you should get a speed at the bottom of 2.8 meters per second. The next question is, what about the force? What about the tension? Now, for this, you do need to know a little bit about rotational forces. So here we're going to look at what forces are acting on it right here. And so I have gravity, mg, and I have tension. I'm going to call it tension 1 because it's the tension at point 1. Now, at this point, the speed is 0. So what that means is it's not in circular motion at this point. It does have an acceleration. That acceleration is perpendicular to that tension. But what that also means for me is that there is no acceleration in this direction. So what I'm going to think about doing here is I'm going to think about rotating my coordinate system something like this. And so that means I need to resolve mg into components, where this angle is my 60 degrees, the same as this angle here. And so I have mg cosine of 60 here, mg sine of 60 here. So in the y direction, the sum of the forces in my y direction here is going to be 0. Or if we're thinking circular, because it's not in circular motion, the sum of the forces in my radial direction is 0, because the centripetal acceleration is 0, because the speed is 0. And so here I have tension minus mg cosine of 60 equals 0. And so given that my mass is not listed, I forgot to do that, it's 0.2 kilograms. Given that my mass is 0.2 kilograms, my tension should come out to be 0.98 newtons. So just under 1 newton. Now as it swings down, that tension is going to get larger and larger, and when it reaches a maximum speed at the bottom, the tension will also be reaching a maximum. It is at this point, however, that we do have a speed v. Okay, and so at this moment, it's kind of going in part of a circle. So we do have circular motion at this point. So I do want to draw the direction of AC, which always points radially inward or toward my axis of rotation. My forces acting at this point are gravity, mg, and tension T2. Now I can sum up the forces in my radial direction. So I sum up the forces in my radial direction, set equal to MAC. Go ahead and sum up those forces. So I have T2 minus mg equals MAC. Solving for T2, so T2 is equal to mg plus MAC, where I'm going to substitute in v squared over r. And in our case, r is going to be the length of our string. Now stay with me, don't just plug our numbers in, because there is something kind of cool here. So T2, we can factor out an m, so I get m times g plus v squared. Okay, so square root, so I'm going to square that. So I get 2g L times 1 minus the cosine of theta, all divided by L. What happens is our L's cancel. That's kind of cool. And so the length doesn't make a difference on that pendulum. Kind of an interesting thing there. So tension T2, if you do plug in your numbers now, the tension comes out to be 3.92 newtons. And there you have it.